Hi, everyone. Welcome to SETI Live. Our conversation today is about the DART mission. On September the 26th, 2022, a 610 kilogram spacecraft was deliberately crashed into a tiny asteroid called Dimorphos. And this was the culmination of a mission that was called the Double Asteroid Redirection Test, or DART. And observing that impact from planet Earth was a team of SETI Institute scientists and citizen scientists led by our guest today, Ariel Graykowski. Hi, Ariel. How are you doing?
Hi, I'm good. How are you?
Good, thank you. Now, this observation that you all made is going to be published in the journal Nature. And we're going to be talking a little bit about that paper and your observations. First of all, I'd like to welcome all the visitors from really around the world. Thank you for putting where you're listening in from in the comments. We'll read out some of those as we go on. And if you do have any questions for Ariel, about halfway through this half an hour show, we will be taking your questions, and Ariel will be answering them for you. So I thought, Ariel, first of all, congratulations on the paper. Has there been a lot of press? You're being interviewed by all the great and mighty in journalism. That includes us, of course.
Of course, yeah. It's been really fun. Yeah.
Yeah, good. So I thought we would start before we talk about the paper itself and your observations, maybe to give a little bit of background to everyone about why you're observing this and the importance of it. The DART mission was a proof of concept, wasn't it, for something that could be quite important for the future of this planet. So do you want to tell us a little bit about it?
Yeah, definitely. So the DART mission was designed for the goal of planetary defense. And what planetary defense means is basically there are asteroids out in space, and some of them fly pretty close to Earth sometimes. And there's a worry that maybe one of them will hit and will be big enough that when it hits, it will cause a disaster. You heard of the dinosaurs. So we're trying to avoid a situation like that, or even something smaller that could harm anybody in a city at all. And in order to do that, there's been a lot of different methods suggested on how to divert an asteroid or how to perhaps destroy an asteroid before it hits us. And DART, the goal of that was to see if we can hit it and move the asteroid's orbit just a little bit. So that way, instead of it being on a trajectory to hitting Earth, it is slightly moved so that it will just miss Earth. And so that was the goal of the mission. That was the main goal of the mission. So this was kind of different than other NASA missions that you might have heard about, where the goals are some science to get out of it. But in the case of DART, the goal was to test this piece of technology to see if we can defend our planet from asteroids, and then see what science we could pull out of it as well. So it was an interesting mission. And it took off and it was successful. They hit the asteroid and it moved just a little bit. So they proved that they can just crash something into an asteroid and change the way it's moving.
Okay. Now this, in fact, Didymos said we can say a little bit about this. Isn't just this is a special asteroid in itself. It was discovered by the Spacewatch program, I believe, back in the 90s, and the Spacewatch was actually designed to search for these near Earth, these sort of risky asteroids that were coming too close to the Earth. And so that program was successful. It's found a lot of these near Earth asteroids. And Didymos was one of them, but this is a binary asteroid, isn't it? Hence the name for double asteroid from the mission. So it's its own little planetary system, isn't it? In a way.
Yeah, it is. So you have Didymos, which is the primary body, and then it has its own little moon called Dimorphos. And Dimorphos orbits around Didymos, and the whole system orbits around the sun, like everything else in our solar system. And so the DART spacecraft was aimed at the smaller of the two, the moon, Dimorphos. And so it wanted to alter the orbit around Didymos.
So you send it up there, and of course another reason why this asteroid system was chosen is this actually isn't heading towards us. This is, no conspiracy theories here. This wasn't actually a way to stop this from crashing into the Earth. This was a nice, safe asteroid out there, double asteroid system. And we thought, this is a good one to pick. It's not too far away, but it's not too close either. In fact, the sizes of these are tiny, aren't they? They're, I think, Didymos is about 700 meters across. So this is quite a small size, and Dimorphos is tiny. It's about 150 meters, and they're orbiting each other. I haven't memorized these numbers, but I think it's quite interesting to get a sense of scale. And the separation of the two is just over 1 kilometer or just under a mile. So this is a little system, almost like the Earth and the Moon, that are orbiting each other on a much smaller scale. And of course, you want something small, because if you crash one of these, this spacecraft, which is 600 kilograms, into the Moon, it's not going to make much difference. So they chose something little, so it'll make a difference.
Right, exactly. I mean, so this was a test of technology. They didn't want to put every huge piece of mass out in space for it not to work, right? So yeah, you got to try it on something small first.
Yeah, good. And then we can worry about hitting the bigger things later.
Yeah.
I just want to call out some people who are tuning in. Welcome. Bruno is from France. Morty is from, more specifically, Normandy. Welcome. Frank is down in, or up from here, San Francisco. Hi. We've got people listening from Osaka, Florida, Croatia, Columbus, Ohio, Mark from Warwickshire in England, and Dave from Devon in England, and a few slightly more local people of the SETI Institute from San Diego and other places in California. So thank you, everyone, for letting us know where you're calling in from. So when did you all at the SETI Institute and Unistellar decide that you're going to take a look at this impact? What is the planning for this?
Yeah, so in general, we have a team here of SETI Institute astronomers, and we all do our projects using Unistellar data. And so basically, Unistellar is a company that sells telescopes, and you have the option, if you have these small telescopes, to take a scientific observation, which is defined by the scientists. And then you can upload your work to the cloud, and we download it and we do all our analysis with that. And so we all have our little specialties, right? So I typically am in charge of the comets. I define comet projects. And then we have Ryan Lambert, who's in charge of planetary defense. And so we knew that the DART impact was coming. This was a planned mission for a while. And so to prepare for it, we wanted to start observing Didymos ahead of time. So Ryan kind of led the campaign in that and had everybody look at Didymos, try to catch occultations of it, so that way we could try to define its orbit a little bit better. And an occultation is when an asteroid or something moves in front of a star and that star dims just a little bit. And that helps us see where it is in space really accurately. And so he started those campaigns. And he does that by communicating to all the people who have the telescopes and saying, this is why we're doing this. This is what we're interested in doing. And people started rolling in their observations months before the impact.
Mm-hmm. Mm-hmm. Okay. I noticed you do have a Unistellar EV scope behind your left ear, and that's your mirrored images there. There it is.
It's hard to do.
What makes an EV scope, which is quite a small telescope, people can see how big it is. What makes that special? How is that a good instrument to do these sorts of observations? Well, tell us a little bit about the EV scope.
Yeah, sure. So it's small. The aperture size is about 4.5 inches. You can carry it around in a backpack. That's kind of the point of these telescopes, is make it easy to use. So you might be thinking, they're small, how can they get such scientific data? But they have a detector in them, and they will take a bunch of pictures over time, and we can take those pictures and stack them together to essentially create longer and longer exposures and reduce the noise from the background and pull out the signal from whatever we're looking at, like an asteroid. The real power of this telescope, especially for this science case and a lot of our science cases, is the fact that there's a lot of them all over the world. And so we always like to say the sun never sets on unistellar. And it's true. There's always somebody who has a night sky in the world who has a EV scope and can point. I've had experiences where I've gone to our community and said, hey, this just happened in the sky. Can somebody please observe? And within hours, somebody's like, okay, I got it, uploading now. And I'm like, oh, great. Okay. And then here for me, it's daytime. And so it's really cool to just constantly get data like that. But that's the sort of power of it, right? So because we had such a vast network, we were able to monitor for a long time, monitor over any period of time, and have people in the right place at the right time. And that was really key for observing the impact itself.
Right. Say a little bit more about this. So you decided you're going to do it. You're going to observe this impact. Then you've got to, figure out where it's going to be visible from, because, chances are, a lot of people are going to be disappointed because it's during the day or, wrong side of the planet or anything. How did you start assembling your team around the world? And where was it visible from, you found out?
Yeah, so the impact was visible from only certain parts of Africa. And so we didn't have a lot of big professional telescopes there to observe. So it started to get kind of nerve-wracking, and we realized more and more how important it is to have this spread of telescopes. But for example, Keck is in Hawaii. Keck is one of the best telescopes in the world. It's huge, and we would have loved to have that observed, Didymos, during the impact, but it's not in the right place at the right time. And that was the case for a lot of big telescopes. It was also almost the case, and kind of was the case, for space telescopes. So like Hubble and James Webb, they did observe Didymos after the impact, but that's kind of the key there, is the word after. They didn't catch images of the impact itself, because it's kind of hard for the telescopes to keep up with an asteroid that was so close, because the asteroid's moving kind of fast relatively. So even the space telescopes had a hard time keeping up and grabbing those observations. And so we knew we needed to reach out directly to people we knew were in the area. And so we put in a lot more effort for the time of impact to reach out to these groups and these people, and really make sure that these groups knew how to use the science mode on their telescope and how to set it up and how to upload data, make sure you're set up before the impact and get ready. But yeah, so we communicated with most of them directly. And we ended up getting 4 individual observations of the impact itself. So we saw the asteroid go from, just a dot in the sky to really bright, and a poof of dust came out of it during the impact. And we could see that in all of these EV scope observations. That was super cool.
Right. So you got everyone ready, you gave them the timing, you got them set up, and 4 actually caught the actual impact. That's amazing. Could you do you have some of the results to show us for the observations? Because it'll be interesting to just have a look at some of these. These are the images before and after, or before and during.
Before, during, and after. Yeah, that's these images here. So you can kind of read this figure from top to bottom, left to right, like you're reading a book. And so in the very first panel, you could see, again, it's just, there's a small dot in the middle of the screen, and that's Didymos. So that's kind of what an asteroid looks at when we're looking in the sky. Almost just looks like another star, right? And then the impact happened, and we see this much brighter dot on the sky. And as we continue to watch, and this happened rather quickly, we see this cloud coming out of it to the left on the plane of the sky. You'll see as you move from panel to panel, you see that cloud forming and then dissipating as it goes away. And then in the last panel, I do also want to point out, you can see that that dot remains brighter than it was in that first panel. So even though that poof moved out and that caused a lot of the brightening, it was still bright because there was still dust hanging around the asteroid. And that dust is super reflective. So you see a brighter dot than you would if there was no dust. So yeah, this is what we saw.
Yeah. So the central dot that we're looking at, that is the binary asteroid. You can't resolve the 2 objects. and the object in the top left is just that's a background star.
Yes.
And so it's interesting to see, as you said, the during this time, the location of the binary asteroid is moving with respect to the background star, which is very interesting as well, which shows how fast this is moving across the sky. That's wonderful.
Yeah, definitely. Sometimes these asteroids are moving so fast that we have to tell our users to stop recording after a shorter amount of time than usual, readjust, start again, because they'll just move right out of the field. But yeah, you can see it moving along. This is how we identify asteroids too. This is a big part of how asteroids or comets get discovered, because there's little dots in the sky. We can figure out kind of what their orbit is, see if it's a new orbit, because we see it moving amongst the stars. And so all day long, we're constantly looking at tiny dots moving back and forth.
Right.
Yeah.
Okay, that's wonderful. So this is, just this is the photons coming into your detector, and as you say, you can see some of the ejector material, which is forming the sort of surrounding coma, isn't it, around the asteroid itself?
Yes.
What observation? So in your observation, are you measuring the change in brightness over time? So this is a photometric measurements you're doing on the brightness of the asteroid. Yeah,
exactly. And I can show the figure that shows those measurements themselves. It's kind of scary figure, a lot of data points here, but all this is the brightness over time. And so we would measure the brightness by basically taking a circle, putting it over the source, so Didymos, and measuring how much photons, essentially how much flux is coming through that circle. And we assign that a number, and that's called magnitude. And so we can see in this figure here that we have this sort of baseline magnitude, this baseline brightness, and then at the time of impact, that brightness went way up. And that was a super exciting moment for us. When we watched the impact occur, we didn't know what it was going to do, and we weren't expecting to be able to notice it so well. But as you could see in the previous image, we really could see that change. And I remember SETI was streaming it at the time of impact, streaming what was going on. And we had an EV scope user showing their phone screen essentially as they were using their telescope. And they showed the little dot and then the bright dot later. And everybody was like, no way, that didn't just happen. So we had a moment of excitement that went up just like the brightness did. And then you can see it kind of comes back down, but still remains brighter. So that's that cloud of dust moving out of our aperture that we set. So that's it dissipates and then remains to be a little bit bright after that.
Right. And you can see the wonderful astronomical unit of magnitude, which actually gets smaller as things get brighter. So that's not, and that's not a typo. That's the way astronomy works.
Yeah, it's very confusing.
So it had an impact. It blew this stuff, and I think one of the reasons it blew a lot of stuff into space was this is a very loosely packed little ball of rock, isn't it? And I think that surprised people.
Yeah, definitely. In general, we assume asteroids are rubble piles, these kind of loosely packed balls of rocks. But we don't know to what extent. And so this mission was really a cool way to get a good idea of what that extent is and how much stuff comes off, how easy it would be for that to happen. One worry was that it'd be so loose that it would just go right through and nothing would happen. So yeah, it's cool to see that it was solid enough for the spacecraft to hit it, and loose enough to really eject a lot of stuff off of the surface. And again, the Dimorphos is very, very small. And so the gravity on Dimorphos is also very, very small. So like here on Earth, you can't just jump and escape the gravity of Earth and fly off into space, but it's very easy on Dimorphos. So it's easy to kick something off and see that sort of ejected dust that we saw.
Yeah, almost a negligible escape velocity on that stuff. So you just have to touch it and it all blows off. Yeah. So we got some questions coming in. I just wanted to say welcome again to a lot of people tuning in. Jonathan from Florida, Tim from Australia, Maggie from Newcastle, Australia. We've got people tuning in from Belgium, Kentucky, Wales, and I'm just scrolling down the list, Raleigh, North Carolina, Texas, Pennsylvania, and I'm going to grab one more. We got somebody from Austin in Texas. Hi. So we've got a few questions, Ariel, coming in. I'm just going to, as they've been posted by the wonderful behind-the-scenes team, in order of how these have come out. So John Wayne, it's a great name, asks if this 160 meter across asteroid hit the Earth, what would be the consequences? So if Dimorphos had actually been heading our way, would we be in trouble?
The answer would be yes, but it's hard to exactly know the extent because as an asteroid goes through our atmosphere and becomes a meteor, it experiences a lot of friction that heats it up. That's why you see fireballs sometimes, because they get so hot as they're moving through the atmosphere that they vaporize. And a lot of it tends to vaporize before it ever hits the Earth. But this one probably wouldn't completely do that. It probably would cause a little damage. So it would depend on how big it was once it made it through the atmosphere and how high off the ground it exploded, or if it exploded on the ground itself. But there's these scales online that are kind of fun to look up that say things like 100 meter, I have it written down here, like 100 meter size object is scheduled, quote unquote scheduled, likely to hit Earth every 10,000 years. So it's just not very likely that we're ever going to encounter something like that. And then that kind of scales down. If you get bigger and bigger asteroids are less and less likely to hit, more likely to be devastating if they do. And then you have micro meteorites that are hitting us all the time. It's constantly, in less than a second, so we have meteorites hitting us. And so there's this scale that tells you kind of how likely we're going to get hit by something that size and what the devastation would be. It would be kind of fun to look up.
Yeah. I think there's something about if it does reach the ground, the ratio of object size to crater diameter is about 10 to 1. So if you have a 100 meter across object, it's going to be a kilometer across the big hole it makes in the ground. But as you say, that requires them to be quite big to hit the ground in the first place. Okay. So we've got another question, and I've lost the question I was going to ask. So. We'll go to Zapfan. What gases did come out? Describe what was blown out?
Oh, sure. So I think what we saw mostly was dust and not a lot of gas, if any at all. So as far as I know, no measurements of gas have been reported. Basically, in asteroids, we expect there to be a lot less volatiles in general than in like comets, for example. Comets exist much farther away in the solar system where it's cold. It's easy to keep those volatiles. But asteroids tend to be a bit closer to the sun. And so they've been there for billions of years. And so we kind of expect, at least on the surface by now, for a lot of any ices or volatiles to have been sublimated or gotten rid of. But we expect that what we saw was mostly dust, rocks, dirt. Yeah.
There was maybe this is a good follow-up question from RL. Thoughts on comet sublimation?
Sure.
So to sublime, you need, as you say, volatiles. Can you say a little bit more about what sublimation is, first of all, and why that's important in comets?
Yeah, sublimation is a weird word. If you don't know it already, it's like, what is that? But basically, it's a phase change where you start with an ice, and normally you would melt the ice and it would turn into a liquid. And then if it keeps getting hotter, that liquid turns into a gas. But sublimation skips that liquid phase. So it goes straight from that ice, that solid phase, to a gas phase. And this is what's happening in comets. So that's why we see that coma is so bright. And when that's happening, it's also dragging dust off with it, with those gas particles. We do see sublimation here on Earth. Think of like dry ice that experiences that. So we know kind of what temperatures are required and what pressures are required for different materials to sublimate. And so we can understand that in these parts of space that are super cold with low pressure, that this is a very possible thing. And it's also something that has pretty close to direct observations of from 67P, or the Rosetta mission, which looked at a comet and has found new sublimation zones and patches of ice, and also gases that match those patches of ice, right? So that's kind of some reasons why we know sublimation exists, and that we know it's happening on comets, and that it makes sense for it to happen on comets.
Okay, great.
Yeah.
Okay, we have a question from Charlie.
Oh, sorry.
Sorry? No,
I was just going to say, we see less on asteroids. So again, a lot of the ice is just gone already. They've lived a long time close to the sun in the solar system, so we don't see it as much. But it's not, unheard of. There is ice seen in asteroids too.
Yeah. So some asteroids are ex-comets. Is that true? Sometimes, but not necessarily.
When we start talking about the definition of what's a comet, what's an asteroid, I think things get kind of hard to define, because comets can go dormant. They can stop doing that, and they look just like a little asteroid now. Do you call them an asteroid? And sometimes asteroids start sublimating, or something like this happens where they get hit and they become really fuzzy and they look like a comet. Can we call them comets? Main belt comets is a term that is used. Terminology, whatever, they're all rocks in space. They're cool when they get hit or when something happens that makes them fuzzy.
Yeah. Astronomers do like categorizing things. They're
they
almost
do.
as bad as ornithologists or stamp collecting. Yeah, you have to slot it into a box somewhere.
You got to, yeah.
Yeah. So Charlie is interested. Charlie Doyle is interested. What kind of mass and velocity would you need to successfully deflect a Chicxulub asteroid to save the Earth? Now, if we're talking about is a 10 kilometer plus, one of the big ones. I think that's interesting. But one thing is, you want to catch it early, don't you? I think that's probably the case.
Definitely. That is something that the DART team has been emphasizing. We've shown that we can do it, but we need time, right? It took time to build the thing that we needed to build and to launch it and to travel far enough to hit it. So that all takes time. And a lot of the time when something like a fireball happens in the atmosphere, we see these meteor events that you hear about in the news. They were only discovered very shortly before you see that fireball, or they were discovered when we see the fireball. We didn't even see it beforehand. And so that's very common. And so I think something we need to nail down is that assessing where everything is. We got to keep going. We've discovered so many near Earth asteroids and asteroids in general, but there's still surprises. So that's going to be a main thing, is to find these things before they hit us and then start building.
Yeah.
Yeah.
Good. I think we're coming short on time now, so apologies that we don't get to everybody's questions. But what's next, Ariel? The DART mission is history now. What's your next target of opportunity? I mean, it could be any things appear, don't they? But do you have anything planned?
Yeah, so for me, I'm focusing on comets, and there's going to be a couple somewhat bright comets coming up. So I'm going to have the whole network look at those comets. One, I think, is called T4 Lemon or something. They all have these, crazy names. And so I think that'll be cool. We'll see how bright it gets. And also, we also monitor comets to see if they do something like outburst. And recently, there was a comet that we all in the network have grown to love called 29P, which has outbursts all the time. And that an outburst is just like, it's kind of bright and then it gets brighter unexpectedly, which is kind of cool because that's what happened with DART, except it was expected. And so now we have this test case with DART of how to make something get brighter, how to activate an asteroid that we can now apply. Okay, do we see the same physics that we saw in DART to 29P, for example, or is it doing something different? Did it get hit, or is it spinning too fast? What is that? And so it recently had an outburst. So that's something that we've been focusing on now. But we'll continue to monitor comets and look for those kind of things, and also try to predict their brightness in the future.
Okay, wonderful. And when that happens, we'll get you back on the SETI Live.
Sure, yeah.
Thank you, Ariel. Thank you, everybody, for watching. This is a production of the SETI Institute. To find out more about what's happening, please do go to our website, seti.org. That will include the press release of Ariel and her team's observations of DART. And that will give you a link on how to find the Nature article that is coming out, and that's well worth reading. Thank you. We will be back next week, I believe, and do keep tuned to the SETI Institute and SETI Live. Thank you, everyone, and thank you again, Ariel, for joining us.
Yeah, of course. Thank you, everyone.